Welcome to the Deep Dive. Today we're tackling, well, one of the biggest mysteries out there, the Tunguska Event. Happened back in 1908. To me, this is just a fascinating blend of history, hard science, and frankly, a reminder of what's flying around above us.
It really is.
We're talking about the single largest cosmic impact event in recorded human history. An explosion, basically over this super remote part of Siberia, June 30th, 1908. And the scale, just trying to picture it, it's mind-boggling. Research suggests something like 830 to maybe 1,200 square miles of forest just flattened.
Yeah, completely flattened. That's around 80 million trees knocked over like matchsticks. It's an immense area.
But the core thing, the reason we're still talking about it over a century later is the paradox, isn't it?
Exactly. You have this absolutely massive energy release. Estimates are around 10, maybe 15 megatons of TNT equivalent. Huge, but no classic impact crater. Nothing you'd expect from something hitting the ground that hard. So for, well, over 100 years now, scientists have been trying to figure that out. Was it an asteroid? A comet? And why did it cause so much damage without leaving that big hole?
Okay, so let's really dig into this. What's great about our sources today is how they bring together the old and the new. We've got these amazing historical eyewitness accounts from 1908.
Which are fascinating in themselves.
Totally. And we're pairing those with really cutting-edge modern science, microgeological analysis, stuff that's showing evidence of like extreme heat and shock pressure right there in the soil.
And that new evidence, I think, really starts to challenge that standard idea that it all just happened up in the air.
Yeah, it suggests maybe something did make contact with the ground, just not in the way we initially thought. Let's get into it. Okay, so to really get a feel for this, let's go back to that morning, June 30th, 1908, maybe 7:15, local time, and the place. The eastern Siberian taiga. We're talking incredibly remote, sparsely populated. That remoteness is key, right? It's why it took almost 20 years for the world to really know what happened.
Absolutely. Which means our firsthand accounts are mostly from the local even-key people, reindeer herders and some scattered settlers. And even they weren't right at ground zero, maybe 20 miles away, minimum.
And what did they actually see and hear? It must have been terrifying.
Oh, unbelievably so. The accounts describe this brilliant fireball blazing across the sky, sometimes trailing smoke. Then this incredible flash described as being brighter than the sun.
Wow.
Followed immediately by this deafening noise, sometimes like sharp claps of thunder, other times a continuous roar, and the physical effects, even miles out. People reported being thrown, dozens of feet.
Thrown through the air?
Yeah, or knocked unconscious just by the sheer force of the blast wave.
Yeah.
Their homes, often just simple log huts, were heavily damaged or just obliterated.
And the impact on their lives must have been devastating.
Critically so. Especially for the even-key herders. Entire herds of reindeer, their livelihood just perished instantly from the heat flash and the shockwaves.
And even further away, people saw something happening, right? Something big in the sky.
Yes. Reports from further afield mentioned seeing this huge column of smoke and dust rising miles into the atmosphere. Apparently, it just hung there for a very long time after the main event.
So when scientists finally did get there, years later, what did they actually find on the ground?
Well, the first major scientific expeditions, particularly Leonid Kulik's team in the late 1920s, they found this unmistakable signature of a massive explosion. This huge area shaped kind of like a butterfly.
The butterfly shape, right.
That's where those 80 million trees were just snapped and blown over. And the pattern was key. They were all lying radially outwards, pointing away from a central point. Clear evidence of an explosion originating above the ground.
But the very center, the epicenter itself, that's the really weird part, isn't it?
It is bizarre, because right there, instead of a crater, the trees weren't knocked down. They were still standing.
But
they were completely stripped bare. No branches, no bark.
Like telephone poles.
Exactly, just these bare trunks, often scorched, charred from above. That vertical charring is a strong clue, suggests intense heat coming straight down from the airburst point.
And this wasn't just a local event. The energy traveled, like, globally.
Oh, absolutely. The seismic shock, the ground shaking, was picked up immediately by seismographs hundreds of miles away in Russia. But what's truly incredible is how far it went.
Yeah.
The seismic waves were actually registered on seismographs in England. That's thousands of miles away. The mechanical energy literally traveled through the Earth's crust across continents.
That's wild. And the atmosphere reacted to, right? Those weird glowing nights?
Perhaps the most surreal effect. It traveled halfway around the world and lasted for days. We have solid reports, like from an astronomer in Northern Ireland, over 5,600 kilometers away.
Northern Ireland.
Yeah. He noted this bright, persistent, nocturnal glow. Said it was bright enough to read a newspaper by outside even after midnight. Similar bright nights were reported over London, other parts of Europe.
So what caused that? Dust.
Most likely. The thinking is the explosion injected enormous amounts of very fine dust or maybe volatile stuff, tiny ice particles from the object itself, way up high into the atmosphere. This created a layer that scattered sunlight, even when the sun was below the horizon.
It's just amazing that something that big, that globally noticeable, could basically be ignored for so long.
It really is, and the delay was critical. The first proper scientific trip, led by the Russian geologist Leonid Kulik, didn't get to the site until 1927.
Nearly 20 years later.
Almost 2 decades. And you have to think why. World War I happened, then the Russian Revolution, then the Civil War. It just made any kind of expedition into remote Siberia completely impossible.
And what did that delay mean for the evidence?
It was tragic, scientifically speaking. Any primary evidence, like potential meteorite fragments, clues about the object's composition, they would have oxidized, weathered away, been overgrown, just vanished in those 20 years. Kulik found the undeniable proof of the blast, the flattened trees, the epicenter, but no fragments. His expeditions were incredibly tough. Just getting there was an ordeal, and they basically cemented that initial paradox. Huge blast, no obvious impactor.
Okay, so let's shift to the science that tried to solve this paradox. After Kulik and others studied the scene, the main explanation became the airburst theory. What did they think the object itself was like?
Right, so once it hits the atmosphere, we call it a bolide. Based on the damage pattern, the energy estimates, scientists figured the Tunguska object was probably, somewhere between 130 and 165 feet across, maybe 60 meters or so.
So not enormous in asteroid terms, but
moving incredibly fast. Estimates put its speed at around 54,000 kilometers per hour, maybe close to 60,000 miles per hour as it came in. And the way the trees fell, that symmetrical butterfly pattern, suggested it came in at a relatively shallow angle, maybe about 30 degrees to the horizon.
Okay, fast object, shallow angle. And the key to the no crater thing was where it exploded.
Exactly. That became the accepted explanation. The object, most likely a stony asteroid or maybe a meteoroid, just couldn't handle the immense atmospheric pressure at that speed. It didn't make it to the surface.
It broke up high.
It didn't just break up. It essentially detonated, exploded violently high in the atmosphere due to the incredible pressure and heat buildup. The estimated altitude is key, somewhere between 3 and 6 miles up, say 5 to 10 kilometers.
And that explosion released all the energy.
All that stored kinetic energy converted instantly into a massive explosion. Again, 10 to 15 megatons of TNT, about 185 times the Hiroshima bomb's energy. That colossal heat flash and the following shockwave traveled down to the surface.
Flattening the trees.
Flattening the trees in that radial pattern, scorching the ones at the center. But because the source was miles up, no concentrated impact to dig a crater. That was the elegance of the airburst theory.
But there was an alternative idea for a while, right? The comet theory. If it was rock, shouldn't there have been some bits found eventually?
That was the nagging question, and why the comet hypothesis was quite popular for a long time. The idea was maybe it wasn't a rocky asteroid, but a small, fragile comet, perhaps even a chunk of comet ink, which has a known debris stream.
And how would a comet explain the lack of fragments?
Well, comets are mostly ice, water ice, frozen gases like methane, ammonia mixed with dust, much less sturdy than rock. So the thinking was when that kind of object hits the atmosphere at high speed, the intense heat and friction would cause it to completely vaporize.
Just turn into gas and dust way up high.
Exactly. Poof. Nothing solid left to reach the ground, neatly explaining why Kulik found no fragments and no crater. Plus, the comet idea seemed to fit with those glowing night skies, all that ice and dust scattered high up. And the timing worked too, coinciding with the peak of the Beta Taurida meteor shower, which is linked to Comet Ink.
It sounds like a neat fit, but recent events have kind of poked holes in that idea of total vaporization, haven't they?
They really have. These low-altitude airbursts we now know aren't just theoretical. We've seen them happen and we've studied them in detail, and the data fundamentally challenges that assumption.
Like Chelyabinsk.
Chelyabinsk in Tome 13 is the prime example. Much smaller object, maybe 66 feet across. It burst higher up to about 30 kilometers altitude, releasing less energy, about 150 kilotons. But what happened?
Fragments. Lots of them.
Exactly. Loads of meteorite fragments were recovered, including one really big chunk that punched through the ice on a frozen lake and left a 9-meter wide crater underneath. So even a smaller, higher airburst didn't completely vaporize. It fragmented and pieces hit the ground.
And there was another one? Tagish Lake?
Tagish Lake in Canada back in 2000, another airburst around 29 kilometers up. This object was known to be very primitive, very fragile, carbonaceous, chondrite material stuff you'd expect to break apart easily.
And did it?
It did break apart, but it didn't vaporize entirely. It created a huge strewn field on the frozen lake below, and scientists recovered over 10,000 fragments.
Okay, so the big takeaway from these modern events is...
The takeaway is crucial. Fragmentation and the survival of some of that material down to the surface, sometimes even causing secondary impacts. That seems to be the norm for airbursts, not some weird exception. Complete vaporization is probably rare, especially for larger objects.
Which makes the Tunguska no crater situation even more puzzling, right? If smaller things leave fragments and holes, why didn't the much bigger Tunguska event?
Precisely. It sets the stage perfectly for this fascinating new micro-evidence that suggests maybe Tunguska wasn't quite the exception we thought it was.
Okay, this is where, for me, the story takes a really sharp turn. For literally decades, that no crater rule defined Tunguska. It supported the comet idea, the total vaporization idea. But now, tiny bits of evidence from the soil are painting a very different picture.
It's fascinating stuff. This recent research focused on analyzing soil samples collected back in 2008. And they were collected from a really specific spot about 30 centimeters deep, so below the surface layer, taken from the raised rim of a small sort of crater-like depression near the accepted epicenter.
So they weren't looking for big rocks, but for microscopic clues.
Exactly, looking for permanent scars left in the minerals themselves by extreme conditions. And the thermal evidence, the heat evidence, is just incredible.
What did they find?
They found multiple indicators of temperatures far, far higher than you'd get from just the shock wave passing through the air, or even a really intense forest fire. For instance, they found tiny melted quartz microspherules, little glassy balls of what used to be quartz.
And quartz needs serious heat to melt, right?
Serious heat? Quartz, silicon dioxide, doesn't melt until you hit about 1710 degrees Celsius. Your absolute hottest forest fire might peak around 900 C, maybe a bit more in spots, but nowhere near hot enough to melt quartz.
Okay, so that's one indicator. Were there others?
Oh yeah, several.
Right.
They also found partially melted grains of titanomagnetite, which points to temperatures around 1625 Celsius. Partially melted feldspar grains, needing over 1100 C.
Wow.
Plus, these tiny glass spherules made of iron oxide and aluminosilicates, suggesting temps in the 1300-1400 C range. And even carbon spherules, basically cooked organic matter like wood or tree sap, indicating rapid heating to between 800 and 1500 C.
So it's like multiple tiny thermometers buried in the soil, all screaming extreme heat.
That's a great way to put it. Multiple independent lines of evidence, all pointing to the ground itself experiencing incredibly intense localized heating, way beyond what a distant airburst alone could realistically do.
Okay, that's the heat. But you mentioned shock pressure, too. What's the evidence for that?
This, I think, is even more compelling. It points directly to a physical impact. The samples contain clear evidence of what we call shock metamorphism.
Meaning the minerals themselves were changed by pressure.
Exactly. Specifically, they found shock-fractured quartz grains that showed features called planar deformation, features PDFs, and also planar fractures, or PFs.
Right, PDFs and PFs. Can you break those down? Why are they so important?
Think of them as microscopic scars inside the crystal structure of the quartz. They're not formed by normal geological pressure, not even by volcanoes or earthquakes. They are considered diagnostic proof, like a fingerprint of extremely sudden, high-pressure shock waves, the kind you only get from hypervelocity impacts.
Like a meteorite hitting the ground.
Precisely. Or something hitting the ground very, very fast. To create these features, you need instantaneous pressures of around 2 gigapascals, or GPa, maybe even higher.
2 gigapascals. How much pressure is that in perspective?
It's immense. Thousands upon thousands of times normal atmospheric pressure. And critically, it's significantly higher than the pressure you'd expect from just the air shock wave propagating down from an explosion 5 or 10 kilometers up. That air blast loses energy as it travels.
Yeah.
To get 2 GPa at the surface requires something hitting it directly.
So this microevidence seems to contradict the classic airburst theory, or at least complicates it significantly. How do scientists bridge that gap, an airburst that somehow causes ground impact?
That's where sophisticated computer modeling comes in. They used hydrocode simulations, things like Autodyne 2D, and plugged in the standard Tunguska parameters. 60-meter stony object, 20 kilometers speed, 14.6 megaton airburst.
The standard scenario.
Right. And what the model showed was really interesting. As the main body breaks apart and explodes high up, it doesn't just disappear. It creates this downward jetting plume of superheated gas and, crucially, fragments of the original object.
Ah, so like a shotgun blast coming down from the explosion?
Exactly like that. A high-velocity cosmic shotgun blast. The simulation suggested this plume, carrying fragments, could hit the surface at speeds still exceeding 2 kilometers per second. That's hypervelocity.
And that impact would be enough.
Yes. The models show that kind of fragmented high-speed impact would generate the necessary transient conditions, temperatures over 4,000 Kelvin, pressures easily exceeding 2 GPa, right where the fragments hit. Enough to shock the quartz, melt the surfaces of mineral grains, and potentially create small, shallow craters that could easily erode or be missed over time.
So the idea shifts from total airburst, no contact, to something more like a touchdown airburst.
That's a really good term for it. The main explosion is still high up, explaining the broad treefall pattern and lack of a single huge crater. But a significant part of the energy carried by this jet of hot gas and high-velocity fragments does reach the surface and delivers a physical impact.
Leaving behind these microscopic scars.
Precisely. And it fits with other models, too. The Earth Impact Effects Program, when you run the Tunguska numbers, explicitly predicts that large fragments may strike the surface. So, the no crater paradox might have been a bit of a red herring. The impact evidence was there all along, just microscopic and scattered.
Okay, so the microevidence adds this layer of ground impact, but then we go back to the human side, the eyewitnesses, and things get, well, messy again, right? Especially with the direction the object came from.
Oh, absolutely. This is where you really grapple with the limits of historical accounts, especially for something so shocking and brief. People are terrified, confused, their perception of time and direction gets warped. But these accounts are still primary evidence, collected pretty carefully soon after the event by people like Voznesensky at the Irkutsk Observatory. We can't just ignore them.
And these accounts led to a major disagreement about the trajectory.
A fundamental disagreement. The early investigators, like Kulik and later Krinov, heavily relied on reports from settlements along the Angara River, which is quite a distance away. Based on those, they concluded the object traveled roughly south to north. They gave azimuths like 192 degrees or 137 degrees.
South to north. Okay.
That was the accepted wisdom for decades. But when later researchers carefully analyzed the physical evidence on the ground, the direction the trees fell, the symmetry of the burn patterns near the epicenter, that evidence pointed very clearly to a different path.
Me too.
From the east-southeast towards the west-northwest.
Azimuths consistently calculated between 95 and 99 degrees.
Wait, so south to north versus east-southeast to west-northwest, that's not even close. That's like a 40 to 90 degree difference.
Exactly. It's a massive discrepancy. How could the physical ground truth point one way and the eyewitnesses, at least the ones initially focused on, point another?
How do scientists explain that? It's so significant that it led some very respected researchers, like Nikolai Vasilev, who spent decades on Tunguska, to propose a radical idea. Maybe the eyewitnesses weren't all describing the same object.
You mean multiple objects?
Possibly. Vasilev argued that the reports from the Angara River settlements described something visually different, maybe lower, maybe slower than what people closer to the Nizhya Tunguska River near the epicenter saw. He basically concluded the testimonies referred to at least 2, maybe more, large daytime fireballs on the same morning. The Angara bolide and the Tunguska bolide might have been separate events, or at least look completely different from different viewpoints.
Wow, okay. That complicates things. And weren't there other weird observations beyond just the trajectory, things that don't sound like a typical meteor?
Yes, and these anomalous reports are perhaps even harder to fit into a simple, single-object explanation. One really puzzling thing is the reports of precursor sounds.
Sounds before they saw it. How does that work?
That's the problem. Physically, it's very difficult. Light travels much faster than sound. For a super-fast object like a bolide, you should see it long before you hear the sonic boom. Yet multiple accounts, especially from further away, distinctly mention hearing loud, thunder-like noises before the fireball appeared or the main blast was felt.
So what could cause that?
It's a real mystery. Some speculate about electrophonic sounds. Maybe the object interacting with the Earth's magnetic field, creating radio waves that people perceive as sound. Others wonder if the sounds were related to seismic activity somehow triggered by the approaching object's pressure wave, or maybe unrelated tremors happening coincidentally. It's deeply puzzling.
And visually, there were strange reports too, not just a single fireball.
Very strange. We need to list some of these because they really stretch the definition of a standard bolide. For example, the meteorological station at Kesma reported seeing two huge fiery circles in the sky around 7 a.m., right when cloud cover increased sharply just before the main event. What were those?
Fiery circles. Okay.
Then there's an incredible account from Nizhny Karolinsko. Witnesses there described seeing a blindingly bright, white-bluish cylindrical object, they called it a pipe shape, moving downwards, vertically, for about 10 minutes.
10 minutes moving downwards. That doesn't sound like a space rock trajectory at all.
Not even remotely. A meteoroid flashes across the sky in seconds. This description of a slow, 10-minute vertical descent is physically baffling for an incoming object. Then, according to the report, it turned into smoke, and there was a loud knock that damaged buildings.
That's incredibly weird. And weren't there reports of things seen really far away that seemed too low to be the main event?
Exactly. Reports that are very hard to link to the main high-altitude explosion, like from Kamensko, nearly 600 kilometers distant. They saw an oblong body described as if detached from the sun, fly across the sky, and then appear to fall in the northeast. But critically, the sounds they heard seemed to come from underground, suggesting maybe a local seismic event, perhaps triggered by the main shockwave interacting with geological faults in their area. Or another report from near Ilinsk, where a witness saw a flying star with a fiery tail that they claimed actually fell into the water. Again, for a piece of the main bolide to survive, travel hundreds of kilometers and then gently fall into water at low altitude without a huge splash or crater. It seems very unlikely. It suggests something much smaller, much more localized, maybe atmospheric plasma or something else entirely.
And finally, the trail it left behind. Or didn't leave behind. You mentioned Chelyabinsk left a huge, obvious smoke trail.
Yes, a spectacular, persistent trail photographed by everyone. You'd expect something similar, probably even bigger, from the much larger Tunguska object. Yet many Tunguska eyewitness accounts describe the trail as minimal, a bluish strip, a short haze, or sometimes no trail at all.
So, less impressive than expected.
Considerably less impressive than the physics would suggest for a giant object burning through the atmosphere. This lack of a consistent, massive smoke trail adds another layer of complexity. Maybe many witnesses weren't seeing the primary object high up, but rather these secondary, lower altitude, possibly shorter-lived phenomena. The whole picture derived from eyewitnesses is just incredibly fractured and confusing.
Okay, so let's pull back from the specifics of 1908 for a moment. We have this massive airburst, now with evidence suggesting fragments hit the ground, plus all these confusing historical accounts. What's the big picture here? What does Tunguska mean for us living today?
Well, Tunguska wasn't just some historical curiosity. It fundamentally defined a specific type of cosmic threat. It showed us that you don't need a direct, ground-shattering impact to cause continent-scale devastation. An airburst can do it.
And how often might something like that happen?
The estimates are pretty sobering. Based on cratering rates and asteroid populations, scientists figure a Tunguska-scale event, something capable of wiping out a major city or region, probably happens on average maybe once a century, give or take.
What's a century?
And looking specifically at the kind of touchdown airburst the new microevidence suggests, some studies looking at geological traces across Europe estimate that kind of event might happen over Western Europe maybe once every 1,500 years or so. So these aren't astronomical odds. It's a recurrent hazard baked into living on this planet.
And we got a pretty sharp reminder of that hazard just recently, didn't we? With that asteroid 2023 NT1.
That was a very close call and a perfect illustration of the threat. Asteroid 2023 NT1 was estimated to be, 30 to 60 meters wide?
Right.
Right in the Tunguska size range, potential energy around 10 megatons.
Same ballpark.
Exactly. And it passed Earth incredibly close, only about a quarter of the distance to the moon. But the really scary part,
You didn't see it coming.
we didn't see it coming at all. Our global asteroid detection systems only spotted it 2 days after it had already zipped past us and was heading away from Earth.
That's not good. An object that size, capable of Tunguska-level destruction, basically flew under the radar until it was already gone.
It highlights a major gap in our current capabilities. We're getting better at finding the really big extinction-level asteroids, the multi-kilometer ones. But these smaller Tunguska-size objects, the ones that could destroy a city or a region, they're much harder to spot, especially if they come from certain directions, like towards the sun. And there are vastly more of them.
And the potential consequences. If Tunguska, that 12-megaton blast, hadn't happened over remote Siberia, but over, say, London.
The models are chilling. An airburst like that centered over London would have caused utter devastation across the entire area within the M25 orbital motorway. We're talking potentially millions of deaths, the complete destruction of a global capital. The stakes are incredibly high.
Which is why planetary defense has become a real thing, right? Not just sci-fi anymore.
Absolutely. The realization of this constant low-level but potentially catastrophic threat has spurred serious action. NASA established its Planetary Defense Coordination Office, the PDCO, back in 2016.
And their job is?
To find these near-Earth objects, or NEOs, track them, calculate the risk, and figure out what we can actually do about it. And that led directly to developing and testing mitigation strategies.
Like the DART mission, the one that hit an asteroid.
Exactly. The Double Asteroid Redirection Test, DART, launched in 2021, successfully slammed into Dimorphos, a small moonlet orbiting the larger asteroid Didymos, in 2022.
And did it work? Did it move it?
It worked spectacularly well, far better than expected, actually. The goal was to test this kinetic impactor technique, basically hitting the asteroid with a spacecraft to nudge its orbit. DART's impact shortened Dimorphos' orbital period around Didymos by a whole 32 minutes.
32 minutes? That sounds like a lot.
It was way more than the minimum benchmark for success. It proved definitively that we now have the basic technology to deflect an asteroid if we find it early enough.
Yeah.
It was a huge milestone.
So we can prevent this kind of disaster.
We potentially can. As the head of NASA's PDCO, Lindley Johnson, put it, and it's a powerful quote, "A collision of a NEO with Earth is the only natural disaster we now know how humanity could completely prevent, if we have enough warning."
So Tunguska, this century-old Siberian mystery, really laid the groundwork for understanding this threat and developing the tools to maybe, just maybe, stop the next one.
In a very real sense, yes. It defined the scale of the airburst hazard and forced us to take it seriously. #outro. So, wrapping this all up, when you put everything together, the sheer scale of the blast felt globally. The really specific micro-evidence like shocked quartz pointing to ground impact, and then layer on those confusing, often contradictory eyewitness reports. You get a picture of an incredibly complex event.
Yeah, not simple at all.
No. It seems increasingly likely that Tunguska wasn't just a high-altitude airburst that vaporized completely. It was probably more of that touchdown airburst scenario, where high-energy, high-velocity fragments from the disintegrating object actually reached the surface, delivering intense localized heat and pressure.
So this deep dive really shows that even after more than a century, there's still so much nuance, so much more to learn about what happened. And it underlines why we need to stay vigilant, especially against these smaller but still massively destructive airburst threats. They're the ones most likely to surprise us. And here's a final thought for you to chew on, something that stems from those really weird eyewitness accounts. Given those reports of localized things, fiery circles, pillars of fire, things seen far from the main path, maybe even those precursor sounds. What if Tunguska wasn't just about the incoming space object itself? What if it was a more complex interplay? Could the intense shock wave from the bolide have somehow interacted with the local geology? We know there are deep faults in that region, triggering secondary atmospheric or even terrestrial luminous phenomena. Maybe the event wasn't one thing, but a cascade kicked off by the bolide. Definitely something to think about.